we're going to make a similar function like this. Something like that. Let me see how's the notes. Goes up, down, up. Okay. Okay. So we want to know the length of this. So what I'm going to do is, where is the formula coming from? Where is the Arclength formula? Okay. So saying that always. So this is calculus integration. We always start with a partition. So just like Riemann sums. So we make a partition. So let's say let's make a big partition like this. So you go here, 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 and let's say that. Okay, they're supposed to be. Well, let's make it here. They're supposed to be the same distance. Okay. So this is x0, this is x1, this is x2, this is x3, this is x4, and so on. Let's say xn. Okay. So this is x0. So you find this point, you find the image here. Okay. And so this guy is gonna be, this is f of x. The function is f of x. So this point is f of x0. This the equivalent over here, right? So this point, well, I can say, probably can say better. So this point over here is f of x0. This point over here is f of x1. This point over here is f of x2, and so on, right? So this point in particular is x0, comma f of x0, correct? Now this point over here is x1, f of x1. This point over here, x2, comma f of x2, and so on. Okay. So my function, let's make it orange. This function is f of x, okay? Y equals f of x. So we want to know the Arclength between, let's say this is A and this is B. So what we do is pretty much as we do with the left Riemann sum or the right Riemann sum, okay, the approximation. So we want to approach the length. So the length will be this length plus this length plus, let's say this is over here, this length, then this length, and then finally this length. Okay, so notice this is a very bad approximation, right? So it would be better if I had more, but my partition is smaller. So for example, in the notes, this is the partition. You see, so that partition is a little bit better. Okay, but I'm doing count this on purpose. So you say they're saying the point pi is, they're saying pi is x, y, 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 right? So p0, p1, p2, All those are my x0, y0, x1, y1, and so on. Okay, so it's same thing that we're doing. I'm just doing it over here. So this guy is P0 in the other node. Okay. Now, so I need to find the distance, right? So I need to find a formula to find the first one. What do you guys think? How can I find this distance from here to the other point, from x0 f of x0 to x1 f of x1, or if you want from p0 to p1? How could we find this distance, guys? What do you guys think? Do you have a formula that does something like that from high school?
The Pythagorean theorem.
Pythagoras theorem, correct. So we need to make a triangle. So you made this triangle and you made this triangle. So let me put a loop. And so we're gonna find that guy over here. So this is let's say this is P0 and this is P1, right? And then I put in these points over here and let's put these points over here. Right? So this guy is this guy. So question, how much is this? How much is this?
F of x1 minus f of x0.
Say again, please.
F of x of 1 and minus f of x of 0.
Okay, so let's do the bottom, the horizontal one. What do you think is this one? Over here. But
x1 minus x0.
x1 minus x0, yes. Because this distance, I need to find this distance. And you see, this is x1 minus x0. So this is x1 minus x0. And this is distance. So really it should be the absolute value. x1 minus x0. But yeah, I'll probably put just x1 minus x0 in absolute value. Because it could be negative. So distance is positive. So I want to avoid those. For example, at the end, I might have negative. So its distance is positive. So what is the vertical one? What is this one?
fx1 minus fx0.
Yes, correct. So this will be f of x1 minus f of x0. Or I could call it like y1 minus y0. Absolute value, right? Absolute value y1 minus y0. So what is this distance? Let's call it C1 to use Pythagoras theorem. What will be C1? So C1 will be what? Let's use Pythagoras theorem. C1 squared equals? What does it say, Pythagoras? Pythagoras say CAB, then you get C squared equals A squared plus B squared, right? So what I should do here, C1 squared equals what? What is A?
X1, x0 squared.
Yeah.
What is
Absolute.
it? Absolute value?
Of x1 minus x0 squared.
Squared, correct. Plus absolute value y1 minus y0 squared. But then I don't, of course, I need the C1, but I don't need C1 squared. I need C1 only. So I just take the root, square root, and then I get the distance. So this guy is C1. So this guy, let me raise this guy. This guy is C1. This guy is C2. This guy is C3. This guy is CN. Okay. C4 here, well, C4 here, and Cn, okay? So what is my approximation? Well, my approximation is this C1, right? So my approximation is doing it like my approximation, length approximation. My length approximation is C1 plus C2 plus C3 plus Cn, correct? That's what I'm saying here. So I found C1, but we can do C2. And put it in another color. C1, C2, C3, C4, etc. until Cn. Okay, so that's what I found. But I found that I have formulas for this. So I could do, instead of writing that, and this is good because this is going to be the beginning of series. So we can write this like a series, and that's what we have been doing, the partial sums. So this is the sum of Ci from I equals 1 to n. We have been using that notation for partial sums, remember? Okay, so let's see in the notes. So let's compare with the notes. So you can go, when you go to the notes, you see, you know, you have some fancy notation, but look at distance. Instead of distance, I call in the absolute value, because that's what really it is. And this is just the square root of xi minus 1 squared plus yy. So this guy is Ci. So let me see if I can write on this. I want to write on this. No, okay. So this guy is what we are calling. It's not letting me write on it. No. Okay, so this guy over here, the whole thing is called Ci. Okay, let me see if I can write this. No, sorry, not letting me write in on this. So if I change in my notation over here, if I change the 1 by I, so I'm going to change it by I. So this is Ci will be xi minus xi minus 1 and then plus yi minus yi minus 1. Okay? So I have a formula for the Ci's. We're almost done. Okay, so keep up. So I just changed my notation to this notation now. You see? I do it for the first one, but I can do it for any. Okay. So now we can change the notation again, and this is normal in physics, normal notation in physics. So you cannot really complain because that's what your faculty from engineering and physics are gonna do. So xi minus 1, all this one. I wish I could annotate, but no. So No, it's all right. I'm trying again to do it, but it doesn't let me. Okay, well, so I have my sum of CIs, right? So now I can use the notation from physics, and then I'm gonna do. He's doing something weird. Sorry, guys, let me stop sharing and share again because something's happened to my computer. Gosh. Okay, now it's working. Okay, now it's working. Okay, so using my notation of physics, I can say instead of xi minus 1, I can say delta xi squared plus delta yi squared. Okay, so this is for your from your physics classes. So now we're gonna use an important theorem that you use in your calculus 1, and you probably thought was useless, and it's the following. So if you have, so this is called the mean value theorem. Mean value theorem. So it says that if you have, we can use just f of x1 minus f of x0 equals f prime of some point in the middle of x1 and x0. Let's say x star 1 times x1 minus x0. So what is this saying? So this is just saying that the mean value theorem says this. If you have a function, let's say this is x0 and this is x1, right? So if you find the secant, the slope of the secant, so what is the slope of the secant? So it will be f of x1 minus f of x0 divided by x1 minus x0. So you see, if I put this guy divided to the other side, this guy is the slope of my red line. Okay? So the mean value theorem says there is a guy in the middle that such that the derivative at that point has the same slope. So look at it. It's right here. So this guy is x star 1. So the slope, the slope of the tangent line at that point is exactly this value. Okay, that's the mean value theorem. So all that to say that instead of writing y1 minus y0, I'm gonna write it f prime of x1 star times x1 minus x0. So we're gonna do that like in the notes is right here. You see, in other words, yi minus 1 minus yi equals f prime xi delta x. And then basically we are done because look at what we're gonna do. So we were saying that my approximation is this guy, right? My approximation is is this guy. That's the sum of the CIs. But every CI is what? Is the square root. This is the sum. I equals n of the square root of xi minus xi minus 1 squared plus yi minus yi minus 1 squared, right? But then we're going to replace this guy by the mean value theorem. So this is sum I equals 1 to n square root of the xi. Well, I said I was using delta x, so let's use the delta x. So I save time. That's why people use that, because you save a lot of time. Delta x I squared, and this will delta y, right? Squared. So instead of that, I'm gonna write plus f prime x I star delta x I, and everything is squared. This is a square, and this is a square. Now I factor the delta x I, so I go sum I equals 1 to the n, factor the delta x I squared. So I get 1 plus f prime x I star squared, right? So now, because this guy has a square and is in the square root, I can take it out. So you got sum of I equals 1 to the n, square root of I'm sorry, I was sneezing. 1 plus f prime x I. Okay, sorry. F prime x I star square, and I'm gonna take the delta x I out. You see? Now we take limits, both sides. So when you take the limit, you are making your rectangles infinitesimal. So when I take the limit n goes to infinity, limit n goes to infinity. So your rectangles are gonna be really small. So that means your approximation, when you are taking the limit, your approximation is gonna be something like this. Little rectangles. So it's really close to the length that you need. But when you take the limit, it's exactly the length that you need. So this is the limit. N goes to infinity. And limit everywhere. Limit n goes to infinity. Then limit n goes to infinity. So when you combine the limit and the sum, what do you get? Do you guys remember? When
The integral.
The integral. So all this work just to say that this is gonna be the integral of the square root of 1 plus f of x, f prime of x squared dx between a and b. Okay. And this is really important when you wanna do similar work with, in electrodynamics or work on surfaces. So this, you see, it took us, I know it's kind of heavy when you sweat the first time, but we had done do a couple of times. But look, took us what, 15 minutes, 20 minutes. But 3,000 years ago or something like that, all that they knew was to find the length of a semicircle and the length of a triangle like this. And look at that. In 20 minutes, we just had done so much more. Any function, any curve like that we can represent the like function, we can find it. So make it your own homework to figure out that the semicircle, the length of the semicircle is pi r, right? Because the whole circle is 2 pi r. So the semicircle will be pi r. So that will be a good exercise for you to practice this. If you don't have it, you don't get it, let me know and we can do it in office hours. But this is, this is so much better than 3,000 years ago. So we have done progress, and you see, you are learning this. Very good. Okay. So, but at the end, you don't have to, it's important for your future classes that you understand this infinitesimal thing, how it works. But at the end, what we just learned was that the Arclength integral between a and b of the square root of 1 plus f prime of x squared dx represent the length between a and b of these functions y of equals f of x. Okay, so we deduce it. You basically prove it. We prove that formula. Okay, so it's very important, very valuable. Okay, so in practice for the exam, so this, because this has the square root, I'm gonna allow you to use calculator, and you can use Simpson's rule or left or right hand side approximation to find it. So let's make an example where we cannot solve the integral explicitly, and we just use Simpson's, for example, Simpson's rule. So we will find the length of the curve. So that's the good thing. You can approximate. So with approximation, you can find any length, any area by approximation. Okay, so let's make this example. This is the example. Set up an integral for the length of the arc of the hyperbola xy equals 1 from the point 1, 1 to 2, 1/2. So this is part A. And part B, so that's what it's saying set up, because you cannot really find this integral. Use Simpson's rule. With n equals 10 to estimate the arc length. Okay, so let me give you 5 minutes for A and 5 minutes for B to see how you guys do, okay? So set up the integral and then we will check it, and then we verify, and then we go to find the Simpson rule after that. So, but first let's do A. So let's do 5 minutes to find A. Okay, so let's set up A. This is a solution. So the function is x times y equals 1. X times y equals 1, right? So you will be able to use your calculator in your exam. It, of course, cannot be the most advanced calculators because there are some calculators just find integrals. Okay, so you cannot use that kind. But any reasonable calculator, you can use it to graph this. But this is to graph. You have done it before. So this is just, this is y equals 1 over x. So this function looks like this. So we need to go from 1, 1 to 2, 1/2. So if I plug in at 1, this is 1, so this is 1. And if I plug in 2, so this is 1/2. So I need to find this. This is the Arclength that I need to find. So my integral should be between 1 and 2, correct? I'm integrating with respect to x. Now, if this is y, so y is f of x, no? Y is f of x. So I need to find my formula. It says square root 1 plus f prime of x, x squared dx. So what I need to do is find f prime x, right? I need to find the derivative. So if this is f of x is this. What is f prime of x? You guys
ln x.
say again?
ln x.
No, f prime.
Oh.
The derivative. What is the derivative of 1 over x?
Is it negative 1 over x squared?
Yes, minus 1 over x squared. So important, yeah, that your mind playing you tricks. So make sure when you are doing this so fast in your exam, you need to, double check your work. You see, it happens to me in the class when I'm looking at something else, then I make mistakes. You see, we need to go back and say, okay, this is f x. F prime is the derivative, so minus 1 over x squared. So then I replace it. And then this is square root of 1 plus f prime. So 1 over x squared. Or minus 1 x squared, right? So I get square root of 1 plus 1 over x to the 4 dx. Yes or no? What do you guys say?
Yes.
Yes, okay. So now let's go to the part B. So finding this integral could be very difficult. I'm not sure we can solve it. 1x to the 4, yeah. Yeah. So my advice to you is just use Simpson's rule for this section. For the Arclength, you just need to plug in, you need to find the value of the length. So you can use Simpson's rule. So we're going to use this Simpson's rule over here. Use Simpson's rule with n equals 10. To estimate the Arclength. So use n equals 10. See, this is what is so important. So this, for example, will be a great exercise for the final, because in one example, I evaluate two things. I evaluate the Arclength formula and also one of the approximation method. You can use Simpson's rule, trapezoid rule, left or right hand sum. and then you can find the integral. So that this will be a great example for the final. So don't think you're not gonna see these guys anymore. So that's what I want to give you the chance to go to your exam number 1 and fix and understand really what you got wrong in the exam. Okay, so let me give you 5 minutes to find this approximation using Simpson rule. So remember Simpson's rule is that goes f plus 4f plus 2f plus 4f plus 2f and so on. But I want you to force your mind to remember. So go ahead or go to your notes or whatever. How you do this using Simpson's rule with n equals 10. I can give you more time, like 7 minutes. So you try to really do it.
Sorry, I think your mic is muted.
Yeah, I'm not talking, I'm just drawing. So yeah, I'm leaving you more time, like 2 more minutes. I just want to start doing my rectangle and all that stuff. Okay, so let's start doing. So you can keep working. I mean, keep working, and then when I get close to what you're doing, so you can check it out. So my partition, because n equals 10, so delta. Remember delta x is b minus a divided by n, right? So that's what I'm getting 1/10. So I had to do 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 1.10 is 2. Okay. So, so this is my x0. This is my x1 and so on. So x1 is, so we can put the formula. Let's put the formula. So the formula for the Simpson, well, let's put it Simpson so you guys know Simpson. So it's delta x over 3 and then go f of x0, that is f of 1. So the next one is 1.1, right? So plus 4 of f of 1.1, then plus 2 f of 1.2, plus 4 f of 1.3, plus 4, sorry, it's not, plus 2 f of 1.4, plus 4 f of 1.5, plus 2 f of 1.6, plus 4 of f of 1.7, plus 2 f of 1.8, plus 4 f of 1.9, plus what? Plus f of 2. That should be what you have. And then this delta x is 110. So this delta x is really 110. So 110 times 1 times 1/3 is 1/30. So this guy here is 1/3 times 10. Okay. So remember, f of x is y is 1/x, right? So f of x is 1/x. So this guy is just 1/1, 4, 1/1.1, etc. 2 over f 1.2. So do you guys have a number? Somebody got it? What number do you get? So the number you should get is something close to 1.4 1321. That's the length. Okay. So the problems we did the previous class, you could also use the Simpson rule. Problems we did for the arc length over here for the exam. Okay. So this problem we did, if you want, you could use Simpson rule. Although this is really easy. This is just substitution. I'll try to make one that is not that hard, but so either way you can find it by hand or do the approximation. So we did 2 examples. So we have done 3 examples. So that's good enough. Okay. So let me finish with the last thing we're gonna do on for the exam, and now we're not gonna figure out this formula. We're just gonna use it. And then we're done. And we'll do probably more some examples next week. This is the last section. Is surface area. Well, let me make a new section. Surface area. So similar to what we had done, we could consider a function f of x and rotate only the function, not the region. I'm not rotating the region. When I rotate, what is region? Region is the whole thing. This is the region. But only rotating the function. That's the graph. If I only rotate the graph, I'll obtain, that's the surface. So if I rotate this around the x-axis, so let's say something like this. I'll think kind of something like a bubble, right? So this is the surface area, where my f of x is this one. Okay, so and then this is from A to B. So my formula for the surface area, when I make rotate the function f of x between A and B around the x-axis, this around the x-axis is the following, and I'm gonna ask only around the x-axis. So surface area of the surface obtained by rotating the curve y equals f of x between A and B about the x-axis is given by, and this is the formula, S equals integral between A and B 2 pi f of x square root of 1 plus f prime of x squared dx. So it's almost similar to Arclength, but you multiply times 2 pi f of x, and then you find that that integral. But I think we can make the example on Tuesday. So we give a little space to